Okay, so we got only two rules of differentiation to begin with out of the 4 or 5 rules of limits. So derivatives are limits, which means that at least one of those 5 limits could be used to compute derivatives as shortcuts. So that's certainly the big point of these rules, is they provide shortcuts computing derivatives of new functions based on now our knowledge of derivatives of functions that are we've seen before. Okay, so we just don't have enough yet to in order to get started. We don't have a lot of functions to do with the rules because we just have too few to begin with. So we just have pretty much nothing but quadratic functions at best. Okay, and we have more to discuss about the derivatives, computing them from scratch, from the definition, and that is, well, actually first the some notation. So new notation. Okay, so f prime of a, let me write first, this is what we already are used to. So the difference is the limit of the difference quotient. Okay, so h is the increment, and we have the average rate of change and the limit of the average rate of change. Another one is to say, write the same way, the same thing, but now concentrating on the interval rather than the increment. So f of x minus f of a over x minus a. The second one is especially, I like the last one, especially because it's kind of less mysterious. I find it less mysterious because really you see the change of y. Well, you say the change of f, but what it is really about is the change of y. Don't forget that y is equal to f of x. So if we're talking about change, then there are two variables, x and y, and the change of x in the denominator, and the change of y in the numerator. So that is literally what is going on, and this is which means that we are talking about the slope. Okay, so change of x is horizontal and change of y is vertical. Okay, so the limit is a tricky part, but it is actually more important to understand with that fraction and where it comes from. It is the slope of 2 points on the graph. If these 2 points are getting closer to each other, then you get your derivative. Okay, but the key is this. Okay, so it is the second formula especially. It's kind of symmetric. So you see the symmetry between x and y. So rather y on the top and y on the bottom. Okay, so you could actually write it as follows. So once again, we have these 2 points. Okay, so I could say that these are, say, okay, how about x and a and x. I could name the other ones like this. Say, how about b and y, why not? Okay, so just to provide you with names, the graph of the actual function is irrelevant at this time, and but that is then the fraction turns into y minus b over x minus a, and this is, I hope now it is clear that we have change of y over change of x. Okay, so once again, the fraction itself is more important than the actual limit, even though the limit is the hard part. Well, maybe that's why. So and that's where that division, that fraction is where the, say, feet per second come from. So if your y is measured in feet and x in seconds, you divide and you have feet per second. Okay, so whether you take a limit afterwards, it doesn't matter. The limit of measured in feet per second will remain feet per second. So anyway, the alternative notation is this: delta y over delta x. Okay, so delta stands, it is the Greek letter for D and stands for difference. So difference over difference. Difference of y over difference of x. Okay, so that's the explanation of the notation, but the notation is the same notation for the derivative, except so it's equal to the same thing, to the limit, but I'm sorry, wrong. What I meant to say is what we're talking about is the limit of this thing. So instead of writing it as like this, okay, we have still the limit, this limit. So but this time we say delta x goes to 0. So y depends on x, which means that if delta x goes to 0, there is a chance that delta y also goes to 0. Okay. So delta x goes to 0, then delta y goes to 0, and we have the same fraction. It's just a different notation, and it is used very, very commonly with once again delta standing for the difference. Okay, and then in the notation for the derivative is also different, produced that comes from this idea. It is delta df over dx. So the notation for the derivative is actually a fraction. So it is not equal to the fraction, but the notation is used that something that looks like a fraction in order to remind you about this, that it is actually a fraction. The derivative is the limit of a fraction, so we could use the notation that looks like a fraction. Even though if you go back to the beginning of calculus, sometimes they thought about it of it as an actual fraction, of a fraction of as they say, infinitely small quantities. Okay, so we divide two infinitely small quantities. They didn't understand limits yet. In the beginning, it was hard to figure out. It took a while. So they thought about like two infinitely small quantities divided by each other give you a quantity that is not infinitely small. But that's pretty much the limit, 0 over 0. And then if you get rid of the denominator, you will have a limit. Okay, so in that sense, we know that we can handle this with limits. This time, all we care about pretty much is just the notation for the derivative. So this is one notation, the other notation. So this is also a possibility. Sometimes when you do not point out what the variable is, it's just f prime. It is the name. So these are two name of the new function. So f naturally is the name of the old function. And then f prime or df over dx is the name of the new function. So that's the new function is derived from the old, and hence the differentiability. So just once again to where delta x, delta y, these are where they are. So this is delta x over here. The run and the rise is, this one is delta y. Okay, so that's where that triangle comes from, and we have the slope. So it is entirely about the notation, and well, that's pretty much it. That the thing is. So these two notations are used interchangeably. Sometimes one of the notations is more preferable. So for example, this is how sometimes things might be used. What we already have discussed, say x squared plus 1. We want to find the derivative. You could write it like this. So there is no name of the function. You actually, inside the parentheses, you simply have your formula. And then you just go on differentiating. Another way to put it is like this. Like this. Okay, so once again, these two different notations, certainly the answer will be the same, but just notation, you use a different one. So once, incidentally, this is Lagrange notation. and the other one Leibniz notation. So Leibniz is the Leibniz, so that notation is older. This one, it goes just back all the way back to the origin of the of calculus, and the Newton himself had the different notation. Or either he didn't really have a lot of notation. Sometimes he would, when he spoke physics, he would use dot above the symbol to indicate the derivative. So if x is your location on the x-axis, then x dot is the velocity. Yeah, x double dot is the. Have you seen this in physics? Maybe. No. Dots. Yeah. So that Newton. That was Newton's notation. But so we stick with these two and use them interchangeably, and you might encounter them freely at different times. Okay. So let's see. So we need more derivative. We We pretty much want to differentiate every function that we know. We want to be able to differentiate, and fortunately all we have to do is just to start with a very few basic functions. What I tried to indicate here, what we need. We're going to need exponential function. Well, the logarithm actually is the inverse of exponential function, so we don't have to worry about it. Trig functions, we don't need all of them. All we need is sine and cosine. In fact, only one, and then everything else, every other trig function is built from it. So sine, cosine, the exponential function, and I'm not going to be doing the actual derivations. So we'll just through experimentation we can pretty much see what is going on. I think we already did the graph for sine. Where is it? I have a bunch of functions here. That's not it. This one maybe? Yeah, here it is. Remember this one? So this is the sine, if I remember correctly. It is the sine. Here's the sine, okay? And now if you look at the graph, as we have promised, the idea of how the derivative is the limit is that when you zoom in on that point, the graph becomes starts to appear like it is a straight line. It appears more or less like a straight line, right? And you can, if we make it to scale, we can, or not, you can actually tell what the slope is. Look at it. What's the slope? Look at the units. Units are messed up a bit.
It's almost 1.
It's almost exactly 1, right? So if I step 0.2 to the right, and then they go up, it's 0.2 again. Okay, so the slope appears to be 1, and that actually is the answer. The slope of sine at 0 is 1. So that is one of those so-called famous limits that give us a start with differentiation. So that's number 1 is this limit sine x over x is 1. Okay? In other words, what does it have to do with that, with differentiation? Because this is just a limit, and all you do is just to compare sine with x, as we did it early on. It is, in fact, could be rewritten as limit sine x minus sine 0 over x minus 0. Okay, so because sine of 0 is 0, and then we realize that what we're talking about, actually sine x, is the change of, and so it certainly is still 1, change of y equals sine x, and denominator is still change of x. Okay, so it is the derivative. It is the derivative. So this is the derivative of sine x at x equals 0. Okay, so that gives us only one derivative of all, but it is a starting point. So let me first write out how more notation that we're going to use. This is how we rewrite this statement over here, sine x. And once again, I don't want to write the come up with the name of the function. It's sine x. That is pretty much is the name. So this is if I want to evaluate this function at x equals 0. This is how I write it. I write a vertical line and x equals 0. Okay, so a function, sine x, the derivative of sine, that's the function what it is. And then what we have found out is that the value of this function at, if your x equals 0 is plugged in, you have the answer. Okay. Similarly, if so, I don't have a picture here, but well, we actually didn't do it. Well, if we didn't, let me do it now. So if I replace here cosine, yeah, if I put cosine here instead of sine, what's going to happen? Cosine, unless you remember what the answer is. I'm not sure what happened here. Okay. So it's not zoomed in as much, but you still can guess what. Look at the top point. So ignore those sequences; they don't apply anymore. But if you look at the top point, you can guess what the slope is. The slope is 0. It looks very much like a horizontal line. Okay, so the derivative of cosine at 0 is equal to 1. Okay, so let me, I state that the second famous limit is cosine x prime is derivative at x equals 0 is equal to 0. Okay, so these are the two main trig limits that will produce everything that we need. So let me just run through this quickly. It is so then the rest of the derivative or derivatives. How is it found? It is based pretty much on the trigonometric formulas. So what I need to find is delta as always, delta y over delta x. And it would be, for example, if I want to do sine, it will be sine x plus h minus sine x over h. Okay, and then what happens is I am using the formula for the difference of two angles. I'm sorry, the formula for the sign of the difference. The sign of the difference. And the sign of the difference is equal to sine times sine of the difference times sine of the sum. Okay? So this is, let me just write it out, sine, 2 sine h over 2 cosine x over h. Okay, so just a trig formula. Okay, and then I do a little rearrangement here, and I have sine h over 2 divided by h over 2 times cosine x. Okay, so the tricky part is we ask ourselves what is the limit now? What is the limit of the first term? So it is limit now. We are taking limit with h going towards 0. Nothing happens with cosine, so I'll still have cosine x. What's going to happen with this fraction?
It's going to be 1 over 0?
No. The limit of sine is also 0.
So it's going to be 0 times cosine x is 0?
No. both numerator and denominator go to 0. Right? If h goes to 0, both sine and the denominator go to 0, so it's not going to be indeterminate or infinite. In fact, it is the same as this. So here x goes to 0, and here we have, well, if h goes to 0, then h over 2 also goes to 0. So as you can see, this is the same, these two are the same. Sine of h over 2, well, you can say this is x. Okay, so sine h over 2 or h over 2, where does it go? It goes to 1, because of the first limit. Okay, so then it will be 1 times cosine x, or simply cosine x. So as you can see, that's certainly a nice. Well, I missed the arrow here. Okay, as h goes to 0, it turns out that the derivative of sine, that's what we just discovered. The derivative of sine, now this time it is the whole function is cosine. Okay, let's confirm this algebra. We went through this pretty quickly, but we can confirm the answer with just looking at the graph of the two functions. I will plot sine under cosine, and then I'll compare. So I'll start with sine, looks like this. Okay, so it hits, let me mark things. So this is pi over 2, and this is pi, 3 pi over 2. 3 pi over 2, 2 pi. Okay, and this is 0. Okay, now let me plot cosine and see if it matches in any way. That's right. Well, let me just make sure that everything matched up. Cosine starts at 1. Okay, here. And then at pi over 2 it hits 0. We just saw the graph, and then it goes down and hits 0. Then it reaches its minimum at pi. The value is -1. Then starts to go up again, hits 0, and then reaches its highest point at pi over 2 again, and then it keeps doing it. Okay, so would you see these two match? The match in this sense. So why would the derivative of the first function would be the second function? You see the match?
X equals pi over 2.
Yeah.
It's 0.
Okay.
So we're crossing the
And it matches the 0 slope.
Right.
And we have another one over here. Okay. Anything else? So, well, let me do it the right way. So the value is 0. The value of cosine is 0 here, which matches the horizontal tangent line. Right? Horizontal tangent line, slope 0. Okay? So anything else you see in the other matches?
At 0, the slope's 1. So we start out at 1 on the cosine.
Yeah, so okay, so here the slope is 45 degrees. Well, let's accept it, that's 45, and this is equal to 1. So this is 45 degrees, and the value of cosine is 1. This is -1, by the way, so which means that we have another point like that, this one. Also 45 degrees only going down, and the value is -1. Okay, so that's a match. There is more to it. Yeah?
The derivative of sine x is equal to 1, and cosine starts at 1.
Yeah. No, that's what we just said. There is a more to it. It is actually easier to, rather than actually specifically looking at particular values of the slopes, you can just look at them whether they are going up or down. So if we are looking at the sine function between these two, this is -pi over 2. What is that? It's going up. The slopes are positive. So the slopes are positive, and it matches the positive value of its derivative. Here the slopes are negative. Here slopes negative, and they match to the negative values of the derivative. Okay, and so on. So here it's positive, slope positive, and so on. So that is the most important match between the function and its derivative, is that the increasing behavior, increasing slopes, or rather positive slopes, give you positive derivative, and vice versa. So when you know that the derivative is positive, you know that the slope is positive. Okay, so we'll get to that. But this provides indeed a match between the two functions. Okay, to confirm our computation. But you can probably guess, what about backwards? What about backwards? Well, let's try. What would the derivative of cosine look like?
It's going to look like sine.
No, not quite. Looking at over here, the slopes are what?
Negative.
It's negative, so it's not going to be sine. The sign is positive there.
That's going to be, is it going to be negative sine?
It will be negative sign, right? So let me plot it. So it will look like, it will be exactly, which means simply upside down sign. So it will go like this. No. Like this. Reaches its, no, that's the sign, upside down. Okay. Going down, so negative, right? Reaches -1, goes up, and then repeats itself. Okay, so this is y equal negative sine x. And so this is differentiation. So then the second formula that we need is the derivative of cosine x is negative sine. Okay. There is so that confirms that we have these two formulas. Now we can plug them into the formulas that we have seen, and we'll get a lot of differentiation done. But I don't want to stop here, because what's interesting actually is if we differentiate sine twice, what do we get? Differentiate sine twice. It's here in the picture.
Negative sign?
Negative sign, right. So we differentiate once, you have cosine, second time negative sign. So the notation for the two differentiation is f double prime. Okay. So this is called the differential equation. The second derivative of the function is equal to the negative function itself. Okay. So there are no other functions. Roughly speaking, this is pretty much every function that satisfies this equation is either sine or cosine or their combination. Why is it important? That a differential equation, if you think about it, f double prime. So this is location, and what's the second derivative of location? The first derivative of location is velocity. What's the second? Acceleration, okay. Acceleration, also known as, according to Newton, as, F is equal to am. Acceleration times mass, or ma. Okay, A allocation F. Okay, so the point being is that we are looking at the case when the force is proportional to the location with a negative sign. It is a spring. It is a model of a spring. So if my spring is at the equilibrium here, and I pull it this way off the equilibrium, the force will be pointing in the opposite direction, and it will be the more I pull, the higher the force will be pulling in the opposite direction. So when I release it, what happens? And then it passes by the equilibrium, and then it passes by too far, and then it starts to be pulled back. So what are we getting? What are we getting?
An oscillation.
Oscillation. That's sine cosine for you. Okay. So that's the point of why trig functions to come into play in the first place. We're getting all of these periodic motions, and they're ubiquitous in physics. And this is the spring. The oscillating spring is the most obvious example. Another one is actually a pendulum. Pretty much the same thing. Okay, so these two, and now we could try to apply what we have learned. Say, what is the derivative of sine x plus cosine x prime? Well, sum rule, right? And I have sine x derivative plus cosine x derivative, and cosine x minus sine x. Okay? And then so on. So all the rules apply, and now we could combine trig functions with each other, or trig functions and polynomial functions. All of that is now available. Another famous limit is about the exponential function. So all the exponential functions look like that. Remember, we looked at it. Exponential functions, they all look roughly like that. But remember, we picked one, the most important, based on what? Remember?
E to the...
Y is equal to e to the x, yes. And you remember what is so special about it.
You're always going to hit 1 right there.
No, they all hit 1. All trig functions pass through 0, 1.
Because, yeah.
In fact, we picked it based on the slope. The slope is 1. At 0, the slope is 1. Okay, so that's the choice. I mean, out of all exponential functions, they all vary, and the slopes might vary from almost 0 to infinity, to almost infinity. And we pick one that crosses at 1. Because everything else can be derived from the behaviors of all the rest of the exponential functions can be derived from that of this function. Okay, and it has a very nice property of equal to 1 because, well, can we rewrite this? How would we write this fact? The slope of this graph is equal to 1. How do we write it? Algebraically. The slope of this graph at 0 is equal to 1. How do we write it? Just the way we did it with trig functions, remember? The slope is the derivative, right? So, okay, so what do I write here?
F prime of x equals 1.
Well, so e to the x. So what is that e to the x? I don't want to, and then you have a new function, so suppose it's e to the x. So the slope of this, of the graph of this function is equal to 1 when x equal to 0. So this is prime, that's the derivative, and then I draw once again horizontal line and plug in x equals 0, and the answer is 1. Okay, so that's the other one more famous limit. So where is the rest of the derivative? This is just one value, one slope. We don't know the rest of the slope. So we derived it from algebra again. So I'm looking at delta y over delta x again. So I'll have this, the change of y. Well, tell me, what's the numerator? Change of y, or change of f if you prefer.
Was it f of x minus f of a on top of x minus a?
F of a over x minus a, yeah, certainly works fine. The other one, well, it is actually the limit. No, well, actually, it's not the limit, so we'll take the limit later. I'll take the other one. I'm not sure if it matters, but sometimes you just vary between the two. What? Between these two, the one or the other, they're equally applicable theoretically, but practically, depending on the function, one works better than the other. Remember how we did the quadratic function? For the quadratic function, the second one is better because it's x plus h squared minus x squared over h, okay? And all you have to do is expand. So that's for the quadratic. So you have, that's what we did, x squared plus 2xh plus h squared minus x squared, and then we realized that we can cancel x squared and everything. It was just great, like this, okay? Imagine that if we where am I? Imagine that, hold on a second. Imagine that we use, for the quadratic function, we're using the other one, this one. So it would be x squared minus a squared over x minus a. You still can handle it, right, by factoring. It's just slightly more complicated. So you factor it. Factoring is always more complicated than expanding. Expanding is simply multiplication. You FOIL or whatever you prefer you want to call it, you expand it and just multiplication. It's totally routine. And factoring is sometimes complicated depending on the nature of the function. This one is fairly simple, but so I picked this one. As you can see, it's going to work out pretty well. Ex plus h minus ex over h. Okay, so that is the difference quotient of my function. Okay, at x. Okay, now I want to simplify it. I want to bring the numerator together. What can I do with the numerator? Remember exponential functions? What can I do with the first term? No, I mean you can't really. We're not solving an equation, so we have to use. We can't use logarithm to make life easier. But what happens to the exponent when you have addition on top? What happens to the expression if you have addition at the exponent, x plus h? I can do something with it.
Does it combine?
It is no. You don't you can decompose it into what? Into multiplication. So can you tell me what it is?
E to the x times e to the h.
Ex times eh. Okay. Remember, exponent is simply repeated multiplication. So ex plus h, you multiply e by itself, x plus h times. So, and then that's what you have. X times and then h times, roughly. Okay, so, all right, and now I can cancel, can factor e to the x out. And I have eh minus 1 over h. Okay, so what remains is just to figure out what that limit is. This one, e to the x, and what happens to this limit is... Now, that's a bit tricky, but we should be able to recognize what this is. H is kind of stands in the way, but other than that, it is a familiar expression. No? What? No. No, it's once again, it's the same thing as it is the derivative at 0. Change of y at 1, because, well, I guess what you should recognize is 1 is e to the 0. So it will be e to the h power minus e to the 0 divided by h. That's right, a change of y or change of x. And we know what that limit is. It is once again 1. Okay, so the answer is e to the x, and now that is certainly is a very nice outcome. That the derivative of the exponential function base e That's what makes it so special, is the function itself. So this is the easiest to differentiate function ever. So every other function, well, another function of this kind is 0. If you differentiate 0, you have 0. The rest of them change on the differentiation. But this function is, the derivative of this function is the function itself. And let me once again, to appreciate the result, this is what we're saying. It is also a differential equation. The derivative of f is equal to f. And so the rate of change of the function is proportional to the function itself, at least proportional or even equal to. And that is either, it's called exponential growth, such as population growth, where the increment of population is proportional to the size of the population, because roughly you have equal number of men and women, and then the birth rate is the same roughly. So then you can say that is growing proportionally. So once again, the exponential function and its relatives are the only one that solve this differential equation. So okay, so we have these three functions. For the time being, that's a lot. So we have x squared and some. No, we didn't go beyond the quadratic functions. Quadratic function, sine, cosine, and now the exponential function. Okay. However, what's certainly missing is even this one. We don't know how to differentiate this. Okay, so what is that derivative y? So both of the functions are familiar. Each of them is familiar, but the derivative is not familiar because they are combined in a new way. X plus e to the x we can handle, right? We just split it by the sum rule, and we have x prime plus e to the x prime, and we have 1 plus e to the x. Okay, so that's not hard as long as the operations that we're dealing with is familiar, then we can. But a multiplication of two functions that are not constant, we still don't know how to handle yet. Okay. Well, so we're still not capable of differentiating a lot of things yet, but it is important to early on to understand the reverse operation, or at least be familiar with the issue. That is, every operation in mathematics comes together with its inverse. Remember, every function. So x plus 1, y is equal to x plus 1. The inverse, remember, x is equal to y minus 1, and so on. Y is equal to x squared. X is equal to square root of y. So they all come in pairs, back and forth. Okay, and so they're all algebraic. So that's about with algebraic operations with numbers. So these operations with numbers. Now we are in a very, very different place. We are way, way beyond this. We're not dealing with numbers anymore. So these are numbers, right? X is a number, y is a number. So and that we just reverse from one to the next. Now the new operation. So these are functions on numbers. Okay. Differentiation is also a function, but it's a function on functions. Okay. So look at this. X squared prime is equal to 2x. Okay, so that is a function on functions. So you plug in a function, x squared, and the outcome is a new function. Okay, so that is the challenge of calculus, not just all the computations, but you usually, even though you do see a lot of functions before calculus, but you never produce, or at least not a lot, you don't produce new functions from old. In this fashion, that is very widespread. So differentiation is very important, very widespread, and what is this works? How does it work? It produces new functions from old. Okay, so all right, and so we already know that some rules of how that works out. But then there is a you can reverse. You can reverse. Why do we care about reverse? think motion. So this one is location. You differentiate, you have velocity. You differentiate one more time, and you have acceleration. Okay, but you realize that in any kind of motion, studying motion, it's the exact opposite situation is more common. You know the acceleration, because acceleration comes from force. You know the arrangement, the physics arrangement of things, either gravitation this way, or sun is pulling the Earth towards itself. The forces are known. And then you want to know what's the dynamics of the behavior of, say, or how does the Earth behave around the sun. So it is the location that you don't know, and it means that you want to go backwards from acceleration to velocity, from velocity to location. Okay, that term is called integration. That operation, a new function on functions. In addition to differentiation, to differentiation, the inverse of differentiation. So this is differentiation. We already can do a lot. We have plenty of derivatives known, but actually we at least as much we're interested in the reverse, in going from the derivative to the function. So we're solving the opposite problem. It's like solving equations. So you have equation 2x minus 1 is equal to 7, and you find x. Okay, so it's very easy. If you know what x is, you plug it in and you compute 2x minus 1. But now the inverse problem is to solve an equation. So plugging in numbers into expressions is easy in comparison to solving equations. Even a quadratic equation, think about it. It's so easy to have x squared plus 1 minus x 7x plus 8. I just plug in x equal 2 and I have my answer. That's easy, right? But all you have to do is just to add and multiply, okay? But if you are now reversing the problem and ask yourself, what if that computation produces 0? What is x? You're going in the opposite direction, and you already need the quadratic formula, right? So that compare the challenge of computing that. Not really a challenge computing of this expression when x is equal to 2. You just plug in and you're done in no time. But in reverse, it's hard. So going backwards from the output, which is say 0, and then find appropriate value of x, you need a quadratic formula, and that the comparison is certainly not easy to appreciate because the quadratic formula is sometimes even hard to remember when you see it for the first time. It looks very very complicated, and you go to cubic equations and those formulas. There is a cubic formula too, and it is very complicated. So in other words, the inverse problems are always harder than the direct problems, and that applies totally to differentiation. And then that's why we sort of postpone integration a little bit, at least later in the course, when we're more comfortable with differentiation. But it is simply inevitable, and the hope is that once you have enough experience with differentiation, you will simply recognize a lot of time the outcome. So, for example, if the derivative of the function is equal to 2x, what is the function? X squared, right? So that's roughly, most of the time, a lot of the time, that's how integration works. Okay, it's just having a table of differentiations, and then you just from left to right, and then you just try to find the appropriate entry on the right and go backwards. Yeah.
Now, if you were doing a polynomial,
yeah,
you would never know the true y-intercept, would you?
No, y-intercept is easy. You just plug in 0. It's the x-intercept that's hard, which is very much to that point, yes. Because so y-intercept, it is really that's totally relevant question. It might behave like this, a polynomial of high degree. This is the y-intercept. It is simply f of 0. Okay, so if this is y equal f of x, how do I find y-intercept? I simply plug in x equals 0. Okay, easy. Now, but what about these? I have that to find those, the x-intercepts, I need to solve the equation. So I need to solve f of x is equal to 0. Right? So this will give me the x-intercepts. So that's the challenge of entirely different magnitude. In fact, as you can see, there's only one y-intercept, and there might be as many as, depending on the degree of the polynomials, as many as you like of the x-intercepts, or none. There might be no intercepts whatsoever. So we'll be going back to integration once in a while, just to remind you what this is, the notation. Okay, so we use this integral sign, which is to be explained, but roughly it stands for summation. Summation, and you might remember where we did do summation not a long time ago, when we actually went that exact path. Remember, from acceleration to velocity, from velocity to location, what do? You assume that you know you sample your velocity. How do I find location from velocity? I sample my velocity, and then I assume that during each of those time periods, my velocity is constant. So I multiply the velocity by the time, add, then again multiply the next velocity by time, and add and add and add and add. And that's what we did on the very first time of classes, the day of classes, remember? So broken odometer. Broken speedometer, you use the location to compute your velocity by difference quotient, okay, roughly, to approximate your average velocity. But backwards it is when your odometer is broken and you have your velocity, you have your speedometer and you know your velocity. How do you find your location? Every single, you look at the speedometer as often as possible. Write down, say you look at it every minute, right? So you write down your speed, and then you if you're driving 70 miles an hour, or for the first minute you divide by 60. So that's how far you went, right? Because only 1 minute at a time. Then the next time it is maybe 60 over 60, then 40 over 60, and that is the addition that will give you your location, which amounts to integration. Okay. So, and then we did that by hand. We did it by with Excel as well, and then that is a big deal, naturally. So some of the projects will be about that exactly. Okay, so we are going back to rules of differentiation. Okay, so we have enough, but we will need much more. Well, we don't have enough. We only have two, and these are the two simplest rules, because we have multiplication, addition, and we have composition too. So these are the ones that we have to take care of. But the payoff is that it's not just shortcuts. They're in fact allow us to do differentiation without referring to limits. So this is a big shortcut, and it goes all the way to Newton, even though he didn't use limits, but that pretty much what he did is exactly what we did. It just in different terminology. He used somewhat different terminology. Okay, so more rules of differentiation. Let me start a new one. Okay, so more rules of differentiation. So sum rule once again, f plus g prime is equal to f prime plus g prime. Okay, so so that is the shortened version without the build-up, without the hypotheses or conditions or restrictions. So and it is okay sometimes just to put it in this formula if you are certain that you know what's behind it. And what's behind it is that assume, let's just write it here, assume f and g are differentiable. Then so is f plus g, and then the formula that we have works. Okay, so that's the sum rule. So here, see, notice how I'm omitting this. So f of x, because just this is the shortest version that you can think of. So sometimes it is worthwhile. It is worthwhile, especially once the formulas will get more cumbersome. All of these things that if we can omit them, that we should. So that's why I'm omitting this part. So f is just the name of the function, and so f is the name of the function, g is the name of the other function, f plus g is the name of the new function. So you know how to compute the sum of two functions. So this is, I hope, is unambiguous, right? So, but I want to state also this formula, the sum rule, using the Lagrange notation. I'm sorry, Leibniz notation. This is Lagrange notation. So this is what it looks like. It looks quite a bit different. Certainly, it is the same. The derivative of the sum, that's the shortest version. The derivative of the sum is equal to the sum of derivatives under these assumptions. Okay? Constant multiple rule. So Cf prime is equal to Cf prime. Okay, so once again we assume that f is differentiable at one point or at all points, depending on the circumstances. C is a real number, then so is Cf, and the formula holds. So you have to verify differentiability of the function to begin with before you claim that the product is differentiable as well, and before you can apply the formula. Okay, now Leibniz notation. So remember that we discussed that last time, I believe, when we talked about the first one. We talked about the meaning of the sum of two functions as if we are to have two person or two cars driving in the opposite directions, and we try to figure out how fast they are running away from each other, and that's what the formula explains. All you have to do is to know the velocity of one, the velocity of the other, add them together, and you will know. Okay, so if that's the information you're receiving, the speedometer of one car, speedometer of the other car, then all you have to do is just to know the speed, the combined speed away from each other. You just add those two readings. The second one is also can be interpreted. It's as if it's as if you're covering twice the distance, then your speed is twice as large. Okay, so but there are more complex situations, and that is with other operations, and that is the product. So the explanation is like this. We looked at that a little bit, as if you have a growing rectangle. So, and this is f growing, and this is g growing with time. Okay, so f is growing at a certain rate, known rate. G is growing at a certain rate, also known. The question is, so f is known, g is known. What is f times g prime? In other words, how fast is the the area of this rectangle is growing. So you can think about it some kind of unfurling of some kind of tarp. You can imagine how, and it is moving, it is unfurled in two directions simultaneously, and some people are running in this direction other than that direction, and you want to know how fast the area is growing. Okay, so this is by how much it grows at every moment of time. So first of all, that is the warning that is always is given, that the derivative of the product is not equal to the product of the derivatives. Okay, so f times g prime is not equal to f prime g prime. You can have a number of explanations why this cannot be true. One of them is units. Suppose this is measured in feet, and this is measured in feet. What are the units on the right? Feet, f prime, what are the units of f prime?
Feet.
No, f is feet. F prime?
Feet squared.
Feet, no. It's the velocity.
Feet per second.
Feet per second. Feet per second. Same with g. Also feet per second. Feet per second. Okay, so then altogether it's feet squared per second squared. Okay, on the left, what are the units on the left? The rate of change of the area, what are the units?
It'd be feet squared.
Feet squared for the area itself, and the rate of change of this will be what?
2ft.
No, that's the value itself. That's the product of f and g. It will be measured in feet squared, yes, but the rate of change of it per unit of time. That's what we're talking about. How fast is the area growing? What are the units?
Feet squared
Per second, right? Per second, the area. How many new square feet being added every second, right? So, and that is a mismatch, right? You see the mismatch. This is second here and second squared there. So it is not possible to have a chance of this to work out. Okay, so that extra second stands in the way. And the formula is less predictable, but that's okay. So f prime g plus f g prime. That's the formula. You can notice that how now the units match, right? So on the right, I still have feet per second, feet squared per second, right? In the meantime, f prime g, this is feet per second, and g is feet, right? So feet per second, that's f prime, and g is feet. So altogether, it will be feet squared per second. That's a match. Same thing here. This one is feet, and this is feet per second. So either way, on the left or on the right, we have the same units. Okay, so that works out. And to point out, maybe at least to begin with, where these two terms come from, these are the two terms. This is one term, and this is the other term. So just to, why do you remember that there are two terms? That's why. Okay, so the growth of the area will primarily depend on those two: the horizontal, how far it goes horizontally, as well as how far it goes vertically. Okay, so so I don't want to go. There is a fairly simple proof, but I think we'll skip it, and let's do some, well, time. We'll have a little bit. Let me do one example of differentiation with this formula. So I can do polynomials now. I can do any degree polynomial. So we know that the derivative of x is 1 Okay, and now let's use this formula. Let me write it out. Fg prime is equal to f prime g plus fg prime. Okay, so I just multiply x by itself as many times as I like to find the derivative of all power functions. So x squared, we already know the answer, but let's do it anyway. It is x times x prime. Okay, let's apply the product rule. So that's my product rule. Okay, so let's apply it. The first function x, the second function is x. What do I get?
X prime times x.
X prime times x plus x times x prime. Okay, what is it? X prime is 1. 1 times x plus x times 1, 2x. Right? Okay, let's do x cubed. I'll split it once again into two familiar functions, x squared and x prime. I once again apply the product rule. Okay, what am I getting? Once again, two functions. I differentiate the first. I don't want to differentiate yet. I'll write it out and then I'll differentiate. So x squared plus prime times x plus x squared times x prime. Okay, and we know that derivative of x squared is 2x times x plus x squared times 1. What's the answer? Hold x squared over here. What's the answer?
$3x.
3x squared. So power is growing. Power is growing. One more. X fourth times x prime power rule x third times x, right? Prime times x plus x cubed times x prime. That's not a 1, that's a prime. I will have 3x squared from over here times x plus x cubed times 1, and the answer is 4x cubed. And then at this point we will notice a pattern. You can see a pattern, right? What's the next one? 5x to the 4th, right. Okay, and then 6x to the 5th, 7x to the 6th, and so on. Okay, we'll just do this next time.